Hi guys, we're gonna go into 6.4. We actually skipped 6.3. It's not needed, and again, I told you if it's optional, I'm not covering it just because of the class and how short it is and everything online. So we're gonna go on to 6.4, which is the central limit theorem, which I don't like writing, so I use CLT all the time. It's like combined like terms, but no, it's central limits theorem. And so what it is, it's for all samples of the same size n with n greater than or equal to 30. Now I use the equal to because it can be equal to 30. The sampling distribution of x bar can be approximated by a normal distribution with a mean and a standard deviation. Now here's where it's different. So your mean is going to be mean of x bar, and that's why I make you guys label a lot. So it's the mean of all of the means, and a standard deviation of sigma, I'm gonna write it down here, sigma x bar equals sigma over the square root of n. So essentially this is what happens. I wanna know like the average amount of sleep Mount SAC students are getting, okay? And so what I'm gonna do is I'm gonna randomly pick 30 students. I'm gonna ask them, find an average. And then what I'm gonna do is I'm gonna put them back into the pile of the population, and I'm gonna pick randomly 30 more students, ask them. I'm gonna keep asking students, and I'm gonna take the averages of the averages. Okay, so like if I have 30 averages, I'm gonna take the average of those 30 numbers, and that'll get me this number right here, and then the standard deviation of the same. Now, why do you do something like that? Well, if you're doing one sample, it's not very accurate, but if you're taking multiple samples for multiple people, eventually you're gonna get closer and closer to this true mean value because you're not given it. Okay, and so that's essentially why we do that. Now, we're gonna go ahead and go into this first example. Notice there's not really much, it's just kind of learning about what's happening. So this right here, if you remember from previously, this right here is left skewed or skewed left. And this right here is normal or symmetric, either or. Okay, but here's the thing I want you guys to realize. Notice that it says the number of students. This is obviously more than 30 students, and this is obviously more than 30 students. So I'm gonna say the left graph, and this is not really an example you would get like on an exam. It's more like to understand the problem. So it says the left graph is skewed left, or left skewed, either or. But when we collect data, and find the samples mean, and find the samples mean, the mean tends to be approximately normal. I can spell. Okay, again, this only works if n is greater or equal to 30. If it's less than 30, we got to do some other stuff, which you won't see in this chapter, but I'll still cover it. And then you'll see it for the previous ones. Okay, so here are some key elements, the central limit theorem and the sample distribution of x bar. So here are some key elements. Okay, so this is what you're given. You're given the population when any distribution has a mean of mu and a standard deviation of sigma. You guys know this already. Okay, you knew population is mean and sigma, and then sample was x bar and s sub x. Okay, with the next thing is it's a simple random sample. So remember what's the acronym of simple random sample? We used SRS. With all of the same size n are selected from the population. So what this means is you have a population, and then you have, I pick samples, and I take samples, and I take multiple samples of size n, and we're gonna go ahead and do the math behind it. So here are the requirements. The first one is the population has to be a normally distribution, or n has to be greater or equal to 30. Okay, so the mean of all values of x bar are going to be, so this is the mean. The mean is going to be mu of x bar, which is actually just the answer of mu. It actually makes it a lot easier. The standard deviation is where it changes. So the standard deviation is sigma of x bar, but it's not just sigma. It's going to be sigma over the square root of n. So I'm taking the original sigma, the population sigma, and I'm dividing it by however many samples I took and the square root of that. Okay, and then the last thing, so this is standard deviation. And the last one is your z-scores. So remember your z-score is x minus mean over standard deviation. It's the same thing, so it's still going to be z equals, but it's not going to be x anymore. It's going to be your average. So the average 1 point minus your mean, which is your mu of x bar, over your standard deviation, which is sigma over the square root of n. Okay, so essentially what we're doing is we're taking your z-score and now we're going to convert it into a mean of all means, and that's what the central limits theorem lets you do. Okay, so the notation of sigma x bar is called the standard error of the mean, and sometimes denoted as, now your book gives a standard, like SEM, standard error of the mean. I've seen it as SE, just standard error. Either or works. I just use sigma of x bar. I don't actually write SEM. Not until later. So what happens if the population is not normally distributed, and I'm going to change this to less than. Now I know your book does less than or equal to. I just do less than because 30 technically makes it approximately normal. So I'm going to say, and again, we won't see that in this section. You'll see it for the next chapter and so on. So I'm going to say then the distribution is not approximately normal. And we have to graph, and yes, we do have to graph the data points. Now, again, we won't see this today or in this chapter. Graph the data points and say, and you're going to say no strong skewness and no outliers. Unless there are outliers, but usually you say that. Again, we won't see that for today's lesson or this week's at all, actually. Okay, so let's go ahead and do some, I do want you guys to know what steps to do, and then we're gonna go ahead and try an example out. Okay, so it says, when doing the word problems, take note. And here's like the key word problems. If you're asked to just solve a problem, you don't have to do this, but if you're asked to do a word problem, here are the steps. The first one is you have to say, you have to check the requirements. So there's really only one requirement, but we're gonna go ahead and, so the first requirement is going to be state it's approximately normal if it says it, okay? Or, and if it doesn't say it, you have to say sample size is n equals a blank number, whatever it is, which is greater or equal to 30. So by CLT, it's approximately normal. Okay, and yes, you do have to write, it's essentially this part you have to write out. Okay, individual value or mean from a sample. So I did want to give you guys, like, we did individual for the last chapter, and then now we're going to do sample. Okay, so I did want to give you guys like what the difference is. So for individual, we were asked to find like one person. So this is like one person. Sample is you're looking at multiple. Okay, so for your individual, we're gonna say your mean is your mean, and your standard deviation is your standard deviation, and your z-score is x minus your mean over your standard deviation, and that's it. Okay, whereas in this one, you're given your sample, your mean is not your mean anymore. It's technically your mean, but it's your mu of x bar. Your sigma is sigma over the square root of n, and your z-score is x bar minus mean of x, mu of x bar over sigma over the square root of n. Okay, so you're gonna see the difference in this first example. So it says, the elevator in a car rental building at SFO has a placard stating that the maximum capacity is 4,000 pounds for 27 passengers. That means that 4,000 divided by 27 is 148 pounds, which means that the mean passenger weight of 148 pounds when the elevator is full. We will assume the worst case scenario in which the elevator is filled with 27 male adults. Assume that the adult males' weights are normally distributed with a mean of 189 pounds and a standard deviation of 39 pounds. So I'm going to actually underline some important information. Okay, so I'm going to say they're normally distributed, the mean weight of 189 and a standard deviation of 39. Okay, and how did I get this 148? Well, if I'm saying 4,000 pounds for 27 people, that means that we have 148 pounds per person on average, and that's what mean is. It's average. Okay, so it says find the probability that one randomly selected male has a weight greater than 148. Okay, so this is essentially what we did the last chapter. We found it for one person. So I'm going to write individual, and I'm going to go ahead and follow these steps. Now, it's not really steps. It's the steps from the last chapter. So what was the last chapter? The last chapter was, or the last section was to sketch. So greater than 148. Now the mean is 189, so that means 148 is to the left. And so this is 148, and we're going anything greater than. Okay, so the next thing we're going to do is we're going to go ahead and write out the problem. So the probability that x is greater than 148. And you should see this from the last chapter. And again, this is one person. Okay, so if you want to make a note, you can say from previous notes. Okay, so what did we do after that? Well, our third step was to write normal CDF. And our lower is 148. Our upper is 1,000 because we want everything greater. Our mean was 189 and our standard deviation is 39. So I'm going to go ahead, and probability again is the same as the decimal. So I'm going to do second bars, number 2, 148, 1,000, 189, and 39. And that's my answer. 0.853, and this is for one person. Now the question changes for part B. Part B says for 27 people has a mean weight greater than 148. So essentially it's the same exact question, but this time we're looking at 148, we're looking at 27 people. Okay, so this one right here is using the sample method. Okay, so essentially we're gonna create the first step is the same. Okay, greater than 148, so it's actually the same sketch. But this time, since it's for 27 people, we're gonna do the probability of x bar is greater than 148. Okay, so it's different because of the x bar part. Now we're gonna use normal CDF, but before we use that, let's go ahead and go over some of the notation. So this is the first step, this is the second step, and then the third step is to use normal CDF. But before we do that, we're gonna go over some of the variables. Some of the variables are mu of x bar, and if you look up here, the mu of x bar is actually just your mean. So your mean, it was 189, so we're gonna do 189. And our sigma of x is our sigma over the square root of n. So our sigma was 39 over the square root of 27. Okay, we're not actually going to solve it, but that's essentially what's going to happen. So when we go to our third step, we're going to go and use our calculator, and we're going to go ahead and write this out. So I'm going to write it over here. So normal CDF and everything greater than 148. So it's still the same thing, 148 and 1,000, but my mean is going to be 189. Again, that doesn't change. And my standard deviation, I don't actually have to type this into a calculator to round it. I just have to write it in this part. And so when I type it in, I'm just going to type it in there and it'll calculate it for me. So this right here is going to be your lower, my upper, my mu of x bar, and my sigma of x bar. And I forgot to write that there, so I'm going to write it up here. So lower, upper, and this is mean and sigma. So notice the difference. This is x bar and this is sigma of x bar. Okay, so that's essentially the difference because of the 27 people. Now if this was 13 people, you would write 13. This was 12, then you write 12. Okay. And then we're gonna go ahead and use our calculator. So 148, 1,000, same thing, 189, but this time our number right here is gonna be 39 divided by the square root of 27. And you get 0.9999. So we're actually gonna not write in this to 100, we're just gonna write 0.9999. Even though, I'm gonna write that, even though it's close to 1 or 100%, it's not all the data. So I actually would accept 0.999. That means you're very close, but it's not exact. And then the third or fourth thing, you're supposed to technically do this first, and I'll try to do this first for the other ones, but the first, like the last step is to check requirements. This only happens if it's not 1. If it's greater than 1, you have to check the requirements. And so the only requirement is it states it's approximately normal or the sample size is greater than 30. Now, here's the thing. Do you see how it says 27, which is not greater than 30 or equal to 30, but it says normally distributed. So all I have to say is it says normally distributed, and I'm good to go. Again, I'll try better at putting this first because you're technically supposed to check first before you actually solve. All right, let's go on to, I have 2 more examples. Again, you feel free to try them out and then pause, but essentially there's only 2 more examples left of this section, and that's it. This section's pretty short. So it says, Introduction to Hypothesis Testing. So assume that the population of a human body temperature has a mean of 98.6 degrees Fahrenheit. Forgot the degrees, but this is your mean, so your mu. Also assume that the population standard deviation, I always forget the word deviation. Deviation is 0.62. So I'm going to write sigma is equal to 0.62. If the sample size n is 106, is randomly selected, find the probability of a mean of 98.2 degrees Fahrenheit or lower. Okay, notice we're not asking for a single person, we're asking for 106. So the first thing you actually want to do is you want to check the requirements, because again, that's what we're supposed to do. So check requirements. Again, you don't have to write check requirements, you can just write it out. But the requirement is it's supposed to be, it's supposed to be greater than, equal to 30, or it says approximately normal. Now this question actually doesn't say approximately normal, so we're gonna write out the second part, and we'll write n is equal to 106, which is greater than or equal to 30. So by CLT, it's approximately normal. And yes, you do have to write it like this. And that's it. Okay, check requirement, it's done. It's approximately normal, so we can use the thing. So the next step is to go ahead and we're going to write out, I'm gonna write the important information out to make it more sense. So I'm gonna do this one more like thorough. So the next step I'm gonna do is I'm gonna go ahead and write mean of x bar and sigma of x bar. So remember, your mean is just your mean. So it's gonna be 98.6. Your standard deviation is gonna be 0.62, but over the square root of 106. Again, I'm not solving it, I'm just making sure we know what our variables are. And our third step is to actually solve it the way we've been doing. So we're gonna go ahead and sketch. So we want 98.2 degrees or lower. So 98.2 is already smaller than 98.6 because the middle is 98.6. So I'm gonna say 98.2 and lower. Okay, so we're trying to figure that out. The next thing is we're gonna go ahead and write out the problem. So probability of the mean being less than 98.2. And then what's our third step? Is we're gonna use normal CDF. So normal CDF, and we want lower. So we're gonna go negative 1,000 to 98.2. My mean is 98.6 and my standard deviation, and I'm just gonna write out the formula. And I'm gonna label it, which you should be better at. So this is gonna be your lower, your upper, your mu of x bar, and your sigma of x bar. And I'm gonna go ahead and use my calculator. I'm gonna see what I get. Okay, so I'm gonna do second normal CDF, bars, negative 1,000 My mean is 98, or my upper is 98.2. My mean was 98.6. Oh. And my standard deviation was 0.62 divided by the square root of 106. I'm just going to write that out. So 1.552 times 10 to the negative 11, which is very close to 0, if you want to think about it like that. Okay. All right. So again, pause it if you want to, or try it out on the last example. So it says, when sampling a distribution of X bar, the sample size of 10 are selected at random from a normally distributed population with the mean of 82 and a standard deviation of 7.5. Find mu of X, sigma of X bar, and then the probability of X bar being greater than 70. So the first step is going to be that is the check requirements, because our sample size is 10, so n is 10. So the first thing is, n is obviously not greater than or equal to 30, but it says normally distributed. So I'm going to say says normally distributed. So it actually, that's literally it. Oh, that's all you have to write. We don't have to write check requirements. It's just boom, done. Second step is to find, well, it already tells you to find mu of X and sigma of X bar. So we're going to write mu of X bar, which is going to be just mu of X. And sigma of X bar, if you remember the formula, it's sigma over the square root of n. So I'm going to write 7.5 over the square root of 10. Now, since it asks you to find the values, I'm going to go ahead and calculate it. And so I'm rounding to 3 decimal places, and that's it. Like, that's the second step. So the first thing is find mu of X bar, which I did. Find sigma of X, which I did, X bar. And then now we're going to go ahead and find this one. Now to find this one, the first thing I have to do is I'm going to sketch. So I'm going to sketch it. And 70 is the number I'm looking at. The mean is 82, so that means 70 is like over here somewhere, because the middle is 82, and we want everything greater than that. So we're going to shade to the right. And then I'm going to write probability of X bar being greater than 70. And you're going to get used to drawing a sketch for pretty much every problem you do now. Okay. And how do we do this? We're going to go ahead and use normal CDF. And we want everything greater than 70. So 70s are lower. Our upper is 1,000. Excuse me. Our mean is 82. And our standard deviation, I'm going to actually keep it exact, because the more exact, the more accurate you are. And I'm going to go ahead and label this. This is my lower, my upper, my mean of X bar, and my sigma of X bar. I'm going to go ahead and use my calculator. So second var's number 2. Lower is 70, upper is 1,000, mean is 82, standard deviation is 7.5 divided by the square root of 10. And again, very, very close to 100%, but we're not exactly, so I'm going to just write 0.999. You're good. And that is the end of section 6.4.